Okay, let's start. Okay, so we are studying 6.4 about the Gram-Schmidt process. So the initial starting point is that we are given a set of linearly independent vectors. So we have x1 through x3. Okay, and then by adding one vector at a time, we increase our subspace. The first subspace is spanned by the first vector, and then the second subspace is spanned by first and the second vector, and so on. So we can think about this the sequence of subspace that keeps increasing, like W1, W2, and W3. And then our task was to find each of these subspaces orthonormal set, orthonormal basis, right? So we are basically making these three vectors all perpendicular to each other, right? And then also to normalize the length of each vector as 1. So those vectors were called these guys, U1, U1 and U2, and U1, U2, U3. And then at the end, the span of those three orthonormal vectors, or the subspace spanned by these three orthonormal vectors, will be exactly the same as the subspace spanned by these three original vectors. Okay. And then we studied how we obtained those orthonormal vectors, right? And then now, using this, we will study, or we will learn, another type of a matrix factorization. So matrix factorization, one of the matrix factorization that we studied previously was LU factorization, right? So matrix factorization is given one matrix, we are obtaining some product of multiple matrices, right? So this is a definition or the meaning of matrix factorization. And now, using those U1 through U3, we are now representing our matrix A, which is, or whose column is our basis, using the new basis which are all orthonormal. So let me give an example. Oops. Okay, so let's use this exact same example where we have originally three columns, x1 and x2 and x3. x1, x2, and x3. And then let's assume that they are linearly independent, but not yet orthonormal or orthogonal. And then in the case of an LU, we call the first matrix as L and then the second matrix as U. But now the decomposition that we study is called a QR decomposition. So this guy is Q and this guy is R. Okay, then first of all, by the fact that original matrix A has a linearly independent columns, it can be tall rather than short. So A cannot be like this matrix, because in that case it's not linearly independent, right? And then this is our assumption. Okay, then we now have U1, U2, and U3 as the new columns in matrix Q. Okay, and then what would be the size of an R what will be the size of an R? So for example, it's a 5 by 3, and then this guy is exactly the same as the size of an A, 5 by 3, and then what about the R? What is the size of an R? 3 by 3, right? 3 by 3. Okay. And then let's think about it as a by column. So we start with this first column that has 3 entries, and then what's the role of this column? So we are applying this vector equation type of an interpretation of this matrix and vector multiplication. So first of all, let's call this one as R1 and R2 and R3. All of them are vectors. And then Q times R1. And let's call this guy as an A. And then what will this guy be the same as? I mean, which one? Which one will be the same as this guy? This one will form the first column, right? And then what is the role of those 3 values? They are linearly independent. Linear combination coefficients of these 3 columns in U or in Q, right? Okay, so far so good, right? And then we actually created a U1, U2, U3, which are just orthonormal versions of the basis computed from x1, x2, x3, or a1 through a3, right? And then let's just reconstruct, or let's just think about what are the linear combination coefficients that are forming our first column and then second column and so on. Okay, and then if you remember, how we obtained U1 was as follows. So we first start with the first initial vector x1, and then we normalized it just by having its length as 1. And in that case, this a1 will be u1, u2, u3. So we are obtaining these 3 coefficients, right? And then what would be that coefficient? So first of all, we know how we obtained u1, right? And u1 was just simply this, right? Times this. Okay, and then if we represent a1, and then this guy will become this linear combination coefficient. And then what about u2 or u3? They will be 0, right? And then also, why should these be 0? Are they always 0? I think the answer is yes, because when constructing the first vector a1, okay, and then we made u1 so that the subspace of u1 or spanned by u1 is exactly the same as subspace spanned by a1, right? So we don't need any other basis or any other vectors to represent the original vector a1, right? And so in the place of an r, we can now see those 2 are 0, and then this guy is a1, right? So far so good, right? Okay, and then let's think about the next process or next step that we have gone through. A2, what was the process? So we move on to the second column, and then we first compute the projection of A2 onto the previous subspace, right? So proj W1, A2, right? Then what is this guy? This guy is spanned by U1, right? This guy, right? So W1 is spanned by U1, and then this part, yeah, this part is A2 inner product with 1, and then what? In the denominator, U1 dot U1, right? And then times U1, right? And then here, U1 or U2 or U3, they are all also normal vectors, so their length is 1. So this part can be conveniently become 1, right? Okay, so this part, projection part, is A2 times U1, right? And U1. So we obtain this vector, okay? And then we normalize it, right? In order to obtain U2, okay? Since it's just trivial to just write the normalized version, so I'll just leave it yeah, in your head. And then now this one will become some alpha times U1, U2. Okay, so because this guy is just normalized to make U2, let's call that normalization factor as an alpha. Okay. Okay, in this case, what we do here is to represent A2. So this is an important part. So here, let's represent A2 in terms of the others. And then A2 will be A2 inner product with the U1 and U1 plus some alpha U2. Okay, and then now it is suddenly a linear combination representation using U1 and U2, right? And so here, this part, the first part is this projection part from onto the previous subspace. And also one important fact is projection onto a particular subspace. And then that projection point is exactly inside of our subspace, right? And it means that point is represented as a linear combination of some vectors, linear combination of the basis vectors spanning our subspace, right? And so it is not surprising that this projection part is a linear combination of our basis vector. And then now we are using the basis vectors represented by U1 and U2 and so on. But the first subspace is only spanned by U1, so this one will be our linear combination representation of this projection part. And then the remaining part will form our U2 with some scalar or some normalization factor. Okay, then using this representation, since we didn't add A3 or U3, we can view this guy as this 0 times U3. And so we can now have or represent A2 as a linear combination of U1, U2, and U3. So those linear combination coefficients will form the second column of our R, because the second column in R will work as a linear combination coefficient with respect to U1, U2, and U3, right? And then that will be the same as the original second column. So this guy is corresponding to this, right? Okay, then what is the linear combination coefficient? First of all, the last one will become 0 because we haven't used at all U3. So it's not involving any of U3, so it's such 0. Then what about this guy, the first entry? What will be the first entry? Okay. So it will be this part, right? Because that will be linear combinatorial coefficient for U1. So this one will be A2 and U1. Then what about this guy? This guy is this alpha, right? And this alpha was the remainder, the residuals norm, right? So we have A2, and then we subtract the orthogonal projection part from it, right? And then the residual vector that are always orthogonal to the previous subspace, right? And then we calculate the length of it, and that length will become alpha, okay? And so this part will be the alpha, which is the length of our residual vector. Okay, then let's think about this third column, and then you can now extend this idea and how we construct our matrix R in a way that the first element will become what? First element of R3 will become A3 inner product with U1, right? And then A3, the second one is A3 inner product with the U2, right? And then the last entry here is just another length, the length of another residual vector, right? So here we have an A3, and then we subtract the orthogonal projection part onto the subspace spanned by U1 and U2, right? And then the remaining vector, their length will become this very last entry, okay? So this is a QR decomposition. Okay, so yeah, so here we didn't talk about how we form Q, but how each vector in our Q is just an orthonormal version of our basis, right? And then we already know how we compute these vectors, right? And then while doing so, or in this exact same process, we can just construct our matrix R, right? So that this Q times the first column of an R will form the first column of an A, okay? And then Q times the second column of an R will become the second column of our matrix A. So this is a QR decomposition. And then by looking at this matrix R, so it's a little bit dirty, so let me use another page. So our R, which is a 3 by 3, and then in this case we know the lower part or lower triangular part are all zeros, right? And that's because when constructing the A1, we only used the first basis vector of U1, right? And then for the second one, we didn't need U3 at all, and so we are having this upper triangular matrix, right? So this QR decomposition will give you the orthonormal, the matrix Q as a orthonormal columns, and then R as upper triangular matrix. Okay, so this is the QR decomposition. Okay, then let me ask one thing. Although the QR decomposition assumes that your matrix A, I mean input matrix A, has a linearly independent column. And then what about the linearly dependent column? So you have A1, A2, A3 as 3 columns, and then the second column is actually linearly dependent, or the second column was exactly inside of the previous subspace. So we are thinking about these 3 vectors, but we are thinking about these 3 vectors one by one. And then this one was the first vector, and the second vector was not even the second vector was not linearly independent. The second vector was actually inside of the subspace spanned by the previous vector. And then third vector is having also linearly independent vector. So let's imagine this situation. And then we can compute this Q1 just as usual. And then what about this Q2? Q2. What will be our Q2? What will be our Q2? So if you again, if you think about this Gram-Schmidt process or orthogonalization process, we have a first vector, and then we normalize it, and then the second vector, and then we subtract its orthogonal projection, right, from this original vector. And then if this vector is exactly inside of the previous subspace, and then the orthogonal projection itself will be exactly the same as original vector, right? So we have this kind of plane, and then if we have some point here, and then we can imagine orthogonal projection, right? And then what about this point? Is it already inside of our subspace? And then its orthogonal projection will be exactly the same point, right? And so the residual part will be just a 0 vector. So we cannot even normalize it because it's just a 0 vector. So in that case, we cannot construct non-zero orthonormal vector in the place of Q2, right? So this guy will become exactly 0 vector. So in that case, we do not consider QR decomposition because it will make our matrix Q no longer be orthonormal columns. So that's why we think about only linearly independent case. Any questions so far? Okay, and then probably you will have another homework, maybe this week. But for only with the 2 chapters, like 6.4 and 5. And then you should be able to just train yourself about how QR decomposition works by using some example or exercise problems. Okay, and then let me see. Okay, let me briefly go through the slide. So it's defining the QR factorization, although it's saying it as a theorem, but you don't care much. You don't need to care about the proof of it. It's just you can just take it as a kind of definition, right? So in the case of an LU decomposition, you just took it as a kind of a particular definition of or particular form of a matrix factorization. This is just like that. So we don't need to prove anything here. It's just sufficient to just understand the intuitive process that I just described. And then here we are given a matrix A with the linearly independent columns, right? And then Q is having the same size, and then their columns are also normal columns, and then they will also form the basis for the column space of an A. And then R is upper triangular matrix with the squared size. And then it has additional constraints like positive entries on its diagonal. So it is giving us another constraint that these diagonal part should be all positive. So this is something that we haven't considered, but following this Gram-Schmidt process, all these diagonal entries will be automatically positive values. And can anyone explain why? Why is it true that all these diagonal entries are all positive? Yeah, so how we computed the diagonal entries was we first compute the residual vector, and then we normalize it so that their length becomes 1. And then that residual vector will have positive length, right? So there is no like a negative length vector, right? It's not possible that we have a negative length, and so automatically those diagonal entries are all positive. Okay, so this guy is not something that we have to care about, right? So that is automatically satisfied. Okay, then we have some example here. And then this is the last slide in this chapter 6.4, and this is saying a slightly different situation. So in the case of QR decomposition, given a matrix A, we have to construct Q or U1 and U2 and U3, which are also normal vectors, and that way we form Q, and then we form R as well, right? But here situation is a little bit different. So yeah, we don't know who, but someone actually gave you this Q already. Okay, so in this situation, our assumption is that someone already gave you the also normal basis for your subspace spanned by, or the subspace of this column space of an A. Okay, so in that case, how can we compute R? How can we compute R? So this is quite simple. So we have Q and some R. So this is our unknown, and those two are known, right? And then we can simply multiply Q transpose and Q transpose. And what will be this Q transpose and times Q transpose times Q? Q has an also normal columns, so we have these 3 also normal bases, and then this is Q, and then we have Q transpose on the left, Q1, Q2, and Q3 transpose. And then you guys know only the diagonal entries will become all ones, right? Because that's the self inner product. And those values, okay, off diagonal values will be the inner product between different vectors that are orthogonal to each other. So they will become all 0. So it will just create identity matrix. So this part will be conveniently gone. And so because this is an identity matrix, so our R is just computed simply by just computing Q transpose and A. Okay, so this is a kind of different process. So in the previous process, that is a real QR decomposition. So we construct Q or U's one by one, and then also we construct R, each column of an R, also one by one, right? And then in this case, it's not exactly a QR decomposition, but someone already gave you Q, which are also normal columns that are also the basis for column space of an A. In that case, you can easily compute this matrix R part in this formula. Okay, so that's it for chapter 6.4. Any questions? Okay, now this is the last chapter about our orthogonality. Then the chapter, the name of the big chapter is orthogonality, and this least squares. And this least squares is the one that we studied finally, and this is really important. And that's really like a entry, or that's kind of an entrance to all the statistical machine learning and also deep learning and artificial intelligence. So this is so important. And probably I have studied this maybe like at least 10 to 20 times while studying or taking many lectures in my undergrad or graduate schools. And this is so common topic and quite important topic. So yeah, I think it's just worth being excited about learning it for the first time. Okay, so the least squares problem is as follows. So the initial story about this least squares is as follows. So up to this point, if you remember what we learned from the very beginning of this class, and then we all started from this linear system, right? So this is a linear system, and then that is, so we learned about their properties, like whether they have always at least one solution for any B, and then whether they have a unique solution or not, and so on, right? But in one cases where the matrix A, the columns of matrix A does not span our entire space, and then for some vector B, we cannot have any solution. So in that case, we have a zero or no solution. No solution exists, right? And then what about this? What about this? So it means, so geometrically, so suppose this plane is our column space, and then if B is outside of our column space, that's when we have no solution, right? And then we now want to solve this problem or this linear system just approximately, okay? Just approximately, okay? And so we don't allow any situations of no solution, okay? We want to obtain some solution anyways, even though this B is outside of our column space. Okay, so this is the main idea of this least squares. Okay, then so in order to solve this problem, let's think about how this is initially outside of our span, right? And then in order to obtain the solution, we can move this point inside of our subspace, right? And so B, now we move B into the inner part or into the subspace of our column space, okay? And then which point will be the most reasonable selection or reasonable choice? We have many possibilities in our plane, so this can be approximately moved to this point or other point. And which one is the optimal one, or which one is the most reasonable one? The reasonable one will be the closest point from the original point to some point in our subspace. Okay? So closest means simply the length between these two, original B and then approximated B, inside of our span or inside of our column span. I mean Okay, and then let's be more mathematically like a formal or mathematically like rigorous. And then how can we represent some mathematical notion of this approximate sense? So how can we mathematically represent how much we approximated? So the approximation can be measured by the length of this vector and some vector inside of our subspace, right? And so we are initially given B, and then also given by the subspace, which is the span of A1, A2, A3. Okay, and then now let's think about the approximated point of B. Okay, so this B hat is approximated point, but here at this point B was not inside of our subspace, but this B hat should be inside of our subspace W, right? And then this W was spanned by the columns of an A. And then any point in our subspace spanned by those three vectors can be represented as a linear combination coefficient, maybe C1, A1, C2, A2, C3, A3. Okay, so at this point, we do not care about whether A1, A2, A3 are linearly independent or dependent. So they can be dependent at this point, but still we can represent any point inside of our subspace as a linear combination of these three vectors, right? And then these three vectors are spanning our subspace, right? Okay, then so this is this is like a vector equation form, right? And then we can also represent it as a kind of matrix equation form as A and A1, A2, A3, and this is our matrix A, and then in the coefficient part it will be C1, C2, C3, right? And then let's call this guy as X. So instead of C, let's use X1, X2, X3. So this is our vector X, and this one will become AX, right? For some vector X. Okay, and then now this AX is our B hat, and this is our approximated version of the original B, right? And then we have to minimize the length between these two vectors, or the difference between these two vectors. So this approximation is represented as B minus B hat. And then we want to minimize the length of this vector, right? And then what would be our control parameter, or what do we change in order to minimize this? So we are changing this linear combination coefficient, right? So B hat can be any point in our subspace, but any point will have a particular linear combination coefficient, right? So we change X in order to achieve the minimization of that length of that vector. Okay, so that is the mathematical representation of the best approximation, or the most reasonable approximation. Okay, and then now it's a B minus B hat is represented as AX, right? Okay. Okay, and then in this case, we know, from this geometric understanding, we know that this AX should be, so, or this B hat should be the projection onto the subspace of this column space of an A, right? And then we project B onto this subspace, right? So this should be our kind of optimal solution, right? Okay, and then this part. So this vector can be, so if we have the orthonormal or orthogonal basis for our subspace, so here our subspace is this guy, and this guy, suppose this column space, which is just a one kind of subspace, suppose this subspace was spanned by maybe V1 and V2. They are orthogonal to each other. In that case, how do you obtain this? So this one is B dot V1 and then V1 dot V1 times V1 plus V2 dot V2 V dot V2 and V2, right? You guys know that, right? But in general, this guy is spanned by A1, A2. For example, if we have a matrix A that have a two column of an A1 and A2. So in this case, since A1 and A2 are in general not orthogonal, so we cannot have the projection. We cannot represent its projection onto that subspace as this form, unless or until we obtain the orthogonal basis. Okay, so in this case, so it is a last part of this chapter, but at this point you can think of about how we can utilize what we learned in the previous chapter. So what if we can obtain the orthogonal basis or orthonormal basis for our subspace? Then we already studied or we already learned how we obtain orthonormal versions of a basis for the same space of a matrix, a column space of an A, right? In that case, from A, we can obtain orthonormal basis, and then we now represent this projection part B hat as this, right? So that is one way, okay, one way. And then now I'm gonna give you alternative way. So this pros co of an A, B. So we have a B here, and then we have subspace here, and then this should be orthogonal projection, right? And then if you remember how we obtained this equation, how did we obtain this? So do you remember this? So we have a B, and then suppose we have a subspace spanned by just the A1. Okay, in this case, we obtain this. So this guy, like a C, the projection, orthogonal projection, can be represented as a linear combination, like C1 and A1, and then B minus C1 and A1. Right, so this is a vector, and this is a scalar, and this is a vector, and this guy, or this residual vector, should be orthogonal to A1, right? And so it is becoming 0. So B times B inner product with the A1, and then C A1 A1. So this is dot product. So we divide it here in both sides, right? So that's how we derived this kind of formula, right? Okay, and then now we do the same thing. So this B hat or AX, which is just a linear combination representation. And then we now consider the residual. What is the residual? B minus B hat. And this B minus B hat should be orthogonal to any vector in our subspace, right? So orthogonal to the subspace means you pick up any vector in our subspace, and then that vector and this the residual part or residual vector should be always orthogonal to each other. So in this subspace, and then you have this this residual vector, and then you look at this angle or that angle or this angle, and then it is always the case that the angle should be 90 degrees. You pick up any vector from your subspace, and then the residual vector and that vector should have 90 degrees or perpendicular to each other. So this guy should be orthogonal to A1 and also A2, right? And then let's represent this guy as this A transpose, A1 transpose, A1 transpose and B minus B hat should be 0, and A2 transpose B minus B hat should be 0, right? So we have to at least satisfy these two conditions. Okay, so far so good, right? And then, are they enough condition or are they sufficient condition? So initially our subspace is spanned by A1 and A2, and then we only show that, we only consider just two cases. This is a residual vector, and that is orthogonal to the first basis vector and then the second basis vector. Okay, and then can we say that by satisfying these two, is it always true that this residual is perpendicular to any vector that you choose from your subspace? Can we say that? So again, we have two basis vector, and then we have a subspace spanned by these two, and then we are considering this orthogonal vector or residual vector after projecting one point to here. And then we have this vertical vector, and then we just make this vector satisfy. It is orthogonal to this vector and this vector, and then will this vector also be orthogonal to this vector or that vector, that vector? Is it always true? Is it always true? So that is the answer is yes. Answer is yes, and this is because. So if you think about any other vector, for example, maybe vector y, and in this vector y will be always represented as a linear combination of our basis vector, right? So this is a general form of any vector that you choose from your subspace. Okay, in this case, let's think about its inner product with B minus B hat. Okay, and then you guys know this guy is computed with the inner product with this, and this guy is computed. It's inner product with the computed with the second one separately, and then we add them together. And then for each one, we already showed that this part and this part is orthogonal, and this part, and this vector is orthogonal to each other. So this is coming from these two conditions, right? And then each of these parts will be always orthogonal to our vector, and so we can conclude that those two conditions are just sufficient conditions to show our vector is actually orthogonal to any vector that you choose from your subspace. Okay, so these two conditions are now represented as a matrix form. So again, A1 transpose B minus B hat, and A2 transpose B minus B hat should be 0, right? And then let's just combine these two equations as just one single equation. How can we do that? So we will do this kind of trick. So we have one vector here and one vector here, and then this is another vector, this is another vector, and these two are the same, right? And so we represent it as this. So we have A1 transpose, A2 transpose, and now we bring this guy here, which is a common part. So that common part is B minus B hat, which is a kind of a residual part, right? And then this guy is just one single common vector, right? Then what will be the resulting vector dimension? It is just a two-dimensional vector, and then if we set both of them are 0, then the first one is like, yeah, this guy times this guy will become 0, which is the same as this guy times this guy becomes 0, right? So that will form our first equation, and then, yeah, the second one being 0 is formed by this one, okay? So this is just a kind of convenient form, or just a simpler form of this matrix version of matrix equation version. Okay, then yeah, we are almost at the end of understanding this least squares. So this guy is now A transpose, right? Because our A was composed of the columns, the columns of a matrix A was composed of this A1 and A2, right? This was our original matrix A. So this part will be A transpose, okay? Then now the second part is B minus B hat equals 0, okay? And then what was B hat? So although we don't know exactly what these linear combination coefficients are, but B hat is a orthogonal projection, and then this guy should be belonging to our subspace W, right? So let's just plug that in to this part. So this one is AX, okay? And then A transpose B minus AX equals 0. Then let's just rewrite it as this one. Okay, so let me just change the left and right hand side part. Okay, so suddenly we obtain this equation or linear system. And what was that? So let's be more high level in terms of what we did in this part. So we wanted to solve this, right? Just approximate. So after moving one point which is outside of our span or outside our subspace, we actually moved it to the closest possible point inside of our span. And then what? And then what is our task? We have to solve the x, or the linear combination coefficient, this x, right, by using the columns of our matrix A, right? So this is the main output that we want to obtain, or main output that we want to compute. And this guy is mathematically represented as this minimization problem. And then we know this minimization problem, this B hat should be this orthogonal projection, right? The closest point. And then in order to have this B hat as the closest point, or the orthogonal projection of the original point B onto the subspace of this column space of an A, and then that should satisfy these two equations. And then after just rewriting these two equations, and then we suddenly obtained this one single linear system or matrix equation. And let's think about the size. Let's think about the size of this equation. So A transpose A will be like this, right? So this one will become just two-dimensional, a 2x2 matrix. So this one is A transpose A, right? And then we have unknown or variable one x, right? Then what about the right-hand side? Right-hand side is just the A transpose times B. Okay, so in this case, A transpose times B is just A1 transpose, A2 transpose, and then we have some vector B. So this is the vector outside of our span, right? Outside of our column space. Then we have some basis. Then we just simply inner product with this vector B with each of our bases in our subspace. And that way, we obtain just a two-dimensional, some constant vector. And this is all known, right? Because A is known and B is known, right? So A transpose B is also known vector. And then that vector dimension is just 2. And so we now suddenly obtained this matrix equation. And this matrix equation, let's think about this matrix equation as something like a new linear system as AX equals B. So our new B is this guy, A transpose B, right? And then our new matrix A is actually this, A transpose A. And then now, let's think about the size of an A. This matrix size A, this part A, or A transpose A, will be always square matrix. So it's no longer be like a thin and like a tall, or fat and short, right? It's always a square matrix, right? And then what is the dimension of that square matrix? The dimension is the number of columns in our matrix A. Okay, so what was the role of vector x? X was the linear combination coefficient, right? Associated with each of our columns of A, right? And that linear combination coefficient x, what is the characteristic? What is the property of that x? That x, or that linear combination coefficient, will give you this guy, the orthogonal projection of B onto your subspace. So we are now, our goal is to obtain that linear combination coefficient. Okay, so that the resulting vector is your orthogonal projection. Any questions so far? Okay, so instead of looking at my handwriting, so let's look at the cleanly printed out slides. So this is our final equation that we obtained, just as this guy, right? So this equation has a special name. Okay, so that name is called this guy, normal equation. So this linear system, or this matrix equation, is called a normal equation. And why is it called a normal equation? Is it just a normal or just a usual? Yeah, instead of being abnormal or unusual kind of or strange thing, right? So it's not having that kind of meaning. So normal is, the meaning of this term normal has a mathematical kind of a meaning. What is that? Normal. Yeah, normal is actually the same as a perpendicular or orthogonal or something like that. So in your plane, you consider this vector called a normal vector, and that is in Korean. What was that? normal vector. Normal vector was called a Bobson vector. Bobson vector. So what was that? So that normal vector was actually perpendicular to any vector, right? Any vector to yours, any vector in your subspace, right? Or in your plane, right? So that was the property or definition of this normal vector, right? And then the reason for calling this as a normal equation was because it is almost the same. So if we remember how we formed this equation, it was coming from this, right? So this guy is your normal vector, right? That is perpendicular to any vector in your subspace, right? So that's why we call that as a normal equation. Okay, so again, so this is all, it's a review. So we want to solve this guy, b minus b hat, the normal width, and then this guy is b minus ax, and then right this guy, and that solution is the same as the solution of this normal equation. So in order to solve this least square problem, and that is called a least square problem, and then this least square problem, the solution for that least square problem is the same as the equation for this normal equation. Okay, and then now let's think about this representation. So we have a B, and then we have projection of B onto the column space of an A, and then we have some residual vector, for example R. Okay, and then this guy is called AX, and this guy is actually B minus AX, right? And then so here let's use another notation. So this is our normal equation, and then suppose we obtain the solution for this normal equation, and then that we call this is our assumption. We call this solution of this normal equation as x hat, just by resembling the projection orthogonal projection of B as B hat. Okay, and then corresponding linear coefficient vector, linear combination coefficient, we call that as x hat. Okay, so if we have a solution for x hat, then we can think about we can think about our vector B and its decomposition, the orthogonal projection part and then the residual part, right? And then previously we learned that this guy is exactly inside of our column space of an A. And what about this part? So this part is exactly inside of perpendicular or orthogonal complement of our subspace or column space, right? Okay. So this is one example. So we have two columns and B, and this B is not inside of a column space. So if you just solve it just normally by just doing the Gaussian elimination or this row reduction and then solve it, and then it will give you like a 0, 0, and B or some non-zero. So in that case, previously we would have just concluded that we have no solution. But now we can now have a approximate solution. That approximate solution is computed as follows. So we compute this A transpose A and then A transpose B. And then we now have this square form of a matrix here, and then this another linear system. And then this one will give you the solution. Okay, and then Now let me ask one new question. This normal equation, for example, like transpose A times X equals A transpose B. So this is so special, and this is called a normal equation. And then, would it be possible that this guy will not have any solution? So, yeah, will it be possible that no solution exists here? So at least this is a square matrix, right? A transpose A is a square matrix. Then the question is, still, even if we have a square matrix, our vector B, if that is not outside of columns of these columns of this A transpose A, and then it will still not give you any solution, right? So in that case, we may not have any solution at all, even after we obtain this normal equation. And then, will it be possible? So, will it be possible that there is no solution for this normal equation? So, the rigorous proof will not be given, so I will not prove this rigorously, but let's think about or understand it in this manner. So, what's the meaning of no solution case? So, no solution for X means no solution for or B hat or projection of B onto the subspace do not exist, right? So, no solution case for X will be the same as we cannot find orthogonal projection, right? And then, will there be any case that you cannot find or the orthogonal projection doesn't exist at all for some vector? So we have some subspace, then it could be really small as just one single point as just the origin, and then the entire space will be the biggest one. And then somewhere in the middle, we have this subspace, which is a kind of subset. And then in all these cases, for some vector outside of our, or it could be inside, some vector B, is it possible that we cannot find orthogonal projection of this point onto our subspace? So orthogonal projection is just an orthogonal projection. We just project it onto our subspace, right? So there is no case where we cannot do orthogonal projection, right? So orthogonal projection, we can always do orthogonal projection. Although, in order to compute the exact vector, like as 1, 3, minus 2, I mean, although in order to obtain the exact vector representation, we would have to compute this this kind of equation and so on. But intuitively, the orthogonal projection is always possible. So it's always possible, and so it means our normal equation will always have the solution. Will always have the solution. Okay, because the existence of orthogonal projection. Okay. So we can guarantee that orthogonal projection exists, and then that point can be represented as at least one linear combination using our basis vector, right? Okay, then now we understood that this equation will have at least one solution, And then now the question is, among the three cases, we excluded the no solution case, and then we still have to decide whether this guy has unique solution or infinitely many solution. Okay, so is it possible that we have an infinitely many solution? So first of all, orthogonal projection will be just a unique point. It will be unique. So we can always do the orthogonal projection, and then it is not, at the same time, it is not possible that we have a different or multiple versions of an orthogonal projection. Orthogonal projection is always unique. Okay? So that point is unique, but the linear combination representation of that unique point, will it be possible that we have a multiple linear combination representation for that point? Is it possible or not? Is it possible or not? So this question is quite straightforward. So yeah, we can just forget about all these orthogonal projection and anything, and then we are now given one point, unique point in our subspace. That unique point is exactly inside of our span, right? Inside of our subspace, and then will we have a unique representation or unique linear combination representation using our basis vector, or will we have a multiple representation? And then that problem or that issue will boil down to whether we have linearly independent column or linearly dependent column. So in order to represent one single point in our subspace, this guy, this guy will have a unique solution when when your columns are independent in original matrix A. Okay, and this is when this guy is a special, especially this guy is a square matrix. So when this square matrix form of a linear system has a unique solution, when will that have a unique solution? That should be invariable, right? So this guy should be invariable if A columns of an A are linearly independent. Okay, so I will finish the remaining part in the next class. So that's it for today. Yeah, thank you very much.
I have a question about the homework number 8. I submitted it on the Blackboard. Do I have to send it via email? Is it okay if I don't send it?
If you submitted it successfully to the Blackboard, then you should be fine. And also, I'm not sure if the announcement email was sent, but last night the Blackboard system was down.
Yeah.
So
I had trouble submitting
right. So
it yesterday.
yeah, I'm going to extend the deadline until probably until the end of today.
Okay. I already submitted it.
Okay, that's good.
Okay, thank you.
Yeah, thank you.